Okay, so yay! Hello again. Um, there's a couple things in the chat still going on, but it's mostly about genetics and some Drosophila. That's really funny. Anyway, so let's get started, guys. Today we are going to do chapter 15. We did these first couple things. So we're going to start right off at Friedel Crafts. And I'm going to open up this right next to it so that we could do a little review of last time. So, last time we looked at all of these reactions and we talked about how Friedel Crafts is special because Friedel Crafts have alkylation and acylation, which involve carbon groups, right? And the rest of these reactions are all pretty straightforward. All you really have to know is the reagent, nucleophile, and final product. And the concept I gave you guys is Friedel Crafts will not happen with a strong deactivator or NH2. So we're going to kind of figure out what that means. And blah, blah, blah. Unless anyone has any questions on what we did before. So instead NH3, I thought, well, NH3 is what it is before it's attached to the benzene ring, so that was just my bad. We would talk about NH2.
Do we need to know the mechanism for the Friedel crafts?
Not really. You just need to know that the intermediate will be a carbocation. So that means you can have rearrangements. And you need to know that for the acylation, it's going to have that electrophile that has a special name that we'll talk about in a second. And it has those two different resonance structures. But other than that, you don't.
Okay. So the electrophile for the alkyl group, is that the carbocation?
I'm so sorry. Could you say that one more time?
No problem. So is the carbocation the electrophile?
Yes, it is. So for the alkylation, the carbocation is going to be the electrophile. And, okay, so I'm glad you brought up the other question about Friedel Crafts because I want to review the acylium ion real quick. So the acylium ion is the electrophile for the acylation. And all you really need to know is that there are two resonance structures. One of them is more stable, which is this one, but both of them are showing you the exact same thing. So if he says, which of the following is the acylium ion, both of those are correct. But if he says which of the following is the most stable version of the acylium ion, we have to pick this, and it's because the charge is on the oxygen instead of on the carbon. Cool. So knowing a little bit more about Friedel Crafts, we have to talk about the limitations. And so we kind of talked about it already, but I'm just going to put it over here. One limitation for the alkylation is that it does not work with NH2 or a strong deactivator. And the other one, which is unique to alkylation, is going to be substitution. And someone asked a question about the last thing that we talked about, so I'm going to open that back up real quick. So these two are both the acylium ion, but this is going to be the more stable one because the charge is on the oxygen. You're very welcome. And then someone said they love the Umbreon costume. Thank you. I have my own little Eevee, but he hates me. So. And okay, so a couple people were asking why is poly substitution a limitation? And it's because it happens even when you don't want it to. So sometimes you don't want it to have multiple substitutions. You just want one substituent to be added. But Friedel Crafts is a little bit tricky, and it can cause unwanted poly substitutions. So poly substitution is not always bad, but in this case, it can be unwanted, if that makes sense. Is that a little bit more clear? Yes? Okay, cool. And then I just copied and pasted the strong deactivators thing because it is exactly the same for acylation. And the alkylation actually has one more. And you guys kind of already talked about it. So it can have rearrangements. And the reason it can have rearrangements is because of the carbocation electrophile. And then someone said the NH2 and strong deactivators apply to substituents. Yes, so if the benzene ring already has an NH2 or a strong deactivator on it, you will not be able to then do another reaction and add an alkyl group or an acyl group. Okay, so any other questions? Alrighty. So, for example, someone said, what is polysubstitution? So polysubstitution is essentially just when you add, let's actually do this example, and while we're doing it, I'll explain what then would be considered polysubstitution. So in this reaction, we're going to kick off this group because that is the leaving group, and we will then get this carbocation, right? Is this the most stable possible carbocation for this carbon chain? No, everyone said that's so quick. We can actually do a rearrangement and make this a hydride shift, exactly. And at this point, now benzene can attack. Bam. And our final product then becomes you're attaching to a carbon that is attached to two carbons, so it will look like so. I don't know why I did it going downwards, but whatever, that's just what's going to happen today. So if this were to undergo polysubstitution, now this ring wouldn't just stop there. You would get the reaction occurring again and again and again until eventually the whole ring is covered with these R groups. So this would be polysub. Does this kind of sort of make more sense once you see it doing its thing? And so it said, how do you know if it will keep going or not? So for the purposes of this class, if he asks you for the answer to this reaction, you just want to give him this, right? Just know, because like this is the desired product. Just know that this could be an undesirable kind of product that could be formed by accident. Does that answer your question? And then If NH2 or strong deactivator was present, there would be no reaction. Yes, exactly. But I'm gonna show you guys an example of that later on in a little bit. And then someone said, would it say excess? So he's not really gonna ask you for like this product that would have excess. So he's not really gonna say 1 mole or excess. Just know that this is the desired product, and this is the undesired product. And then where does the bond come from that attaches the benzene to the carbon chain? So that's a really great question. Let's add a page. Sorry that my screen is so all over the place sometimes. So if we have our benzene ring right here, it's going to, and I'm going to skip ahead to the middle step where we already had our carbocation. So the benzene is going to use these electrons and attack here, right? And that means the electrons from that pi bond were used to attach to the electrophile. And then we also have a hydrogen here and a plus here. And then we know that whatever our base was is going to come in and steal that hydrogen and give those electrons back here so that we can reform our double bond. Oh, that was lovely. And so then we get our final product. Does that make more sense? Yes, okay, cool. So for the acylation, it's pretty much the same. The only difference is you can't have any rearrangements because the positive charge is going to be here for the electrophile. And then all we're going to end up doing is adding a bond to where the positive was, and then adding the rest of the group. And so I said, do we need to know the mechanism? You should, in general, know the basic mechanism, but you're not going to have to perform it really on the exam as long as you can look at this and tell me, oh yeah, so all we're going to do is kick off this part and attach the group. All we're going to do is kick off this, rearrangement, attach the group. So that's all you really need for this chapter, but it doesn't hurt to know the mechanism. Okay, so if we scroll on down, I don't know why it says of the following reactions above. Oh, right, duh, never mind. I don't know why that was on a different page then. So out of these two, the next question is which of them could have an undesirable polysubstitution? And we already talked about it. It would only work for the alkylation, not for the acylation. So polysubstitution is only for alkylation. Okay. And for these ones, again, we know that our electrophile will be a carbocation. Is this the best possible carbocation? And someone asked me to go back up. I'll do that as soon as I fix the carbocation. So no, instead of this, what can we do? What kind of rearrangement? We could do a methyl shift. But if we did a methyl shift, we would get this. While that is better, if we did a hydride shift, we could actually just get a tertiary. And so in this case, a hydride shift would be a little bit better. But you're not wrong. We could have done a methyl shift. But the best carbocation would be this one. And so in this case, we actually already have something on the ring, right? And so this group is what kind of group? Sorry, Bear almost fell. It's a ketone, yes, but it is also an electron withdrawing group, correct? And so, wait, something just occurred to me. Did we go over directing effects in SI? Oh, sorry, then I got all mixed up. That's my bad. I was doing it in tutoring, so I assumed we already did it in SI. So we will go back to that. But just for the sake of this example, so this is an electron withdrawing group. So in this case, it is going to be a strong deactivator. So in the case of a strong deactivator, this would not happen. So this reaction would be no, this example, excuse me, would be no reaction. Okay. Yes, I can repeat that. Sorry, I got really confused, so that's completely my bad. I should have done donating and whatever first. But in this case, since this ketone is an electron withdrawing group, it's going to be a strong deactivator, and we know that alkylation cannot happen with a strong deactivator, so this would be no reaction. And then someone had asked me to scroll back up. Ta-da. Did you have a question, or did you just want to see it? Want to see? Okay, cool. So I'll leave that up for a second. Sorry, I don't know why that happened. And then someone asked, can you explain why polysubstitution wouldn't happen for acylation? And yes, I can. So the reason it happens for alkylation and not acylation is because in an alkylation, we add an R group. And an R group is a weakly donating group. And so since we add a donating group, that opens up the opportunity to make the nucleophile more nucleophilic, aka activate the benzene ring. And then that will make the reaction happen again. But in an acylation, you add a ketone group, and that ketone is going to make the benzene ring less reactive, which then is going to not allow it to react again. Does that sort of kind of make sense-ish? And then someone said, did you forget to take away the double bond in the second one? So if you're talking about here, I just gave you the final product here, and then I did the actual reaction mechanism here. And same with here, I just gave the final product, if that's what you mean.
A little bit confused how you got the double bond there again, like through the mechanism.
Oh, like here you mean?
Yeah.
Okay, no worries. So basically what happened in this step is we did an addition reaction, and we ended up with a plus charge, right? So then here we lost aromaticity. So that's really, really bad. So we want to regain aromaticity, and the way we do that is by having our base that was formed when we, like in this first step, when we went from this to this. So we end up with a Cl minus floating around. And that Cl minus, which was the leaving group from our alkyl halide, is going to come in and steal that hydrogen and perform an elimination reaction. So these electrons from this bond right here are going to be given to this bond right here, and we end up with a double bond. Does that kind of make more sense?
Yeah, I get it now. Thank
Okay,
you.
cool. You're very welcome. Okay, so I don't know why I decided to, in this handout, put all this stuff before donating groups or directing effects. So that's completely my bad. Let's switch gears a little bit and work on that, and then we'll go back to the other questions afterwards. So first thing is first, we have to figure out what ortho, para, and meta even means. So if we have some random substituent here, the position right next to it is ortho, one down is meta, and one more down is para. Let me fill that in. And so now when we talk about OMP or ortho, meta, para, you just know that ortho is right next to a substituent, meta is one down, and P is on the other end. That was Bear. He just burped. I don't know if you guys heard that, but finally someone was here to experience it. He literally does human burps. I don't know what's up with that. Any questions about ortho, meta, para before we go on to other stuff? No? Cool. So this is where students kind of tend to get confused by what's an ortho para director, what's an activator, what's a deactivator. So I just want to let you know, directors versus activator and deactivator are different things. So first we're going to talk about what is an activator versus what is a deactivator. So an activator is any group that makes the benzene ring more reactive, aka it wants to react again. And a deactivator is any group that makes the benzene ring less reactive. And as we've talked about, the benzene ring is the nucleophile, right? So we're looking for ways to make the nucleophile more nucleophilic. And when we're talking about electron donating and withdrawing groups, which one of those makes the electron more, the nucleophile more nucleophilic? Electron donating, exactly. So over here we have electron donating groups. And what kind of groups did we have in that category? Like, for example, what kind of charge? Positive or negative? One person said it. Come on, guys, need a couple more answers, please. Okay, cool. So most people are saying negative, and that's correct because in order to donate electrons, you have to have extra electrons lying around, and that would mean a negative charge. Positive charge is actually going to be indicative of a what kind of group? Withdrawing group, exactly. So here we have electron withdrawing group. This is a positive charge. And here we have a negative charge. And so what else kind of identifies an electron donating group? Very important. Okay, so some people said carbonyl groups. Were you talking about donating or withdrawing? Withdrawing, okay, yes. Then in that case, you're correct. So we have carbonyls. And here, someone said it, we have R groups and we have lone pairs. What's another thing in electron withdrawing groups? There's one more big category that I want you guys to remember. Nitro, true, but what I was thinking more along the lines of is halogens. That's very important, and just know that they are under this deactivator group. Okay, cool. So I'm satisfied with this table so far. We'll add more specific things to it as we go on, but this is more than enough for now. Any questions before I scroll a little bit? No? Okay, cool. So we're going to do some resonance real quick, just so we can understand why things are the way they are. So we're going to start out with an alcohol group. And the resonance will start like so, where these electrons will go down, form a double bond, and these electrons are now kicked off to this carbon. And so that would mean we have a negatively charged carbon here, and we have a double bond here, and a plus charge on our oxygen. And let's not forget the other double bonds, they have not changed. In the next resonance structure, we are going to knock these electrons down, move this one over, and so we get, this didn't change. We did add a new double bond here, electrons here, and another double bond. That one we didn't touch. And in the last step, these go here, and these electrons go to this carbon. So we get bam, 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 and a negative charge here. And in the next step, it would just go back like this, leading to our first product, to our first structure, so I'm not going to draw it. But with this, you can notice that we have a delta minus charge here, here, and here, right? Which positions have a delta minus? Ortho and para, exactly. So now we can tell that this alcohol is going to direct ortho and para, because if the benzene ring wants to be the nucleophile, it wants these negative carbons to be where we add our next group. So all we mean by an ortho-para director is that a benzene ring with an OH on it, when we go through another reaction, we will add that next group, ortho and para, to the original group. So in this case, the alcohol is an ortho-para director, as I said. Now, is it an activator or a deactivator? Two people said it. Okay, yes, so it is an activator. And someone asked, can we say that all activators are ortho-para directing? Yes, we're going to talk about that a little bit more in a second. We can say that all activators are ortho-para directors, but we cannot say that all deactivators are meta-directors. Again, we'll talk about that in a second, but that's the general thing I want to say. So over here, we are going to do the resonance, and it's going to be a little bit different. So we're going to move our electrons this way, and we're going to end up with a double bond here, plus charge, and two negatives. And we have to have a positive right here, because we don't have those electrons anymore. In the next resonance structure, we're going to try to compensate for that loss. But now we just have a plus charge here. and these don't change. Next step, we're going to go here. Bam, bam, bam. And I know there's a couple questions in the chat. I'll look at that. Someone asked, how do you know where the partial negative charges go? That's a great question. So the partial negative charges on our benzene ring come from where the negative charges are excuse me, in our resonance structures. So wherever the negative charges land on our resonance structures, that's where we put a delta minus. So as we see, ortho, para, ortho, so we know our ortho and para positions have a partial negative. And so with that logic, in this one, we have the same kind of movement around the ring. The charge is still going to be ortho-para, but now, instead of a negative charge, it's a plus charge. So in this case, we have a delta plus on our ortho and para positions. So that would mean that is very much less nucleophilic. So these positions are really, really bad at being nucleophiles. And so in comparison, the meta position is going to be more nucleophilic. So in this case, it's going to be a meta director. And then someone said, why is nitrogen still positive even after we created the double bond? Valid question. So it's going to be positive because we essentially didn't change the number of bonds that it has. It still has, it went from 1, 2, 3, 4 to 1, 2, 3, 4. And nitrogen wants to have 3 bonds to be happy, so it's still going to be positively charged. You're very welcome. Okay. So please let me know if you would like me to re-explain or repeat anything about meta directors, because I know that one can be a little bit tricky. And I would be more than happy to go over it again. Okay, so we're all clear on meta directors. The reason they direct meta is because we have a positive charge on the ortho and para positions, and so they are really not nucleophilic, and so in comparison, meta is the best. It's the most nucleophilic. Why did my camera do that? That's fine. Alrighty, so this group would be what? An activator or a deactivator? What do you guys think? Deactivator, exactly. And the reason for this is because, as you guys can see, overall, when we added this alcohol, the whole ring got a negative charge, or a delta minus charge. So that made it overall more nucleophilic. But here, we get an overall plus charge across the ring. So that makes it a lot less reactive. So that is why we call that a deactivator. Any questions thus far?
So when we're looking at determining if it's an activator or deactivator, we're not looking at the substituent, we're looking at the benzene ring?
Exactly.
Gotcha.
Okay, cool. And then I, for some reason, didn't give myself enough space to do the resonance for a halogen, so I'm just going to show you guys a pre-drawn one that I did last semester. So a halogen is going to have very, very similar resonance structures to our regular old electron donating groups because it does have a lone pair. And so the resonance goes all around the ring, and we get that delta minus again on the ortho and para positions. So for this reason, halogens will be ortho-para directors. However, they are going to pull electron density away from the ring. So even though it gives delta minus here to the ortho-para positions, overall it is withdrawing electrons from the ring. So that would make it a deactivator. So halogens are ortho-para deactivators. And I'll zoom out so you guys can see it, because I think this is a pretty nice directing effects cheat sheet. Any questions on this? Yes, I can repeat that. So let's go through this one more time, just kind of to give you guys a summary. So up here, we have our ortho-para activators, and I did a resonance for one of them just to give you guys an example. So an example is an alcohol, because it is an electron donating group. So that group has a lone pair. So that lone pair can do resonance throughout the group to give a negative charge on the ortho and para positions. For that reason, we are going to direct future substituents to the ortho-para positions. The reason we call it an activator is because overall it donates electron density into the ring, giving the ring an overall negative charge, which will make it more reactive because it is more nucleophilic. For ortho-para deactivators, these are only going to be halogens, so I'll even write that down. So the ortho-para directors, aka halogens, they are going to, when you do resonance, they are going to give you a negative charge on the ortho and para positions, which means that you will be an ortho-para director because those positions will be the most nucleophilic. However, overall, the benzene ring will be deactivated because it is so electronegative. It pulls electrons away from the ring, like so. And that would mean that overall the benzene ring is less reactive because it has less electron density to be a nucleophile. Meta deactivators, we're going to call strong deactivators, and they are going to direct to the meta position because, as we talked about, they have a delta plus on the ortho and para positions, as we can see. And this would mean that by default or by comparison, the meta positions are going to be the most nucleophilic. And the reason they are deactivators is because they are withdrawing groups, and electron withdrawing groups make overall the benzene ring more electrophilic, and so it's going to be overall less reactive. So zoom out again. Any questions? Does this make sense-ish? Overall, the whole ortho-para versus meta directors, and then activators versus deactivators. Maybe. Yes, okay, I'm glad someone responded because I was like, I think I lost everyone. Also, I'm going to send you guys the attendance sheet because I think I forgot to do that. Whatever, it's not a big deal. That's a joke. It's kind of a big deal. Okay, so now I'm going to scroll up back here, and we're going to talk about this list that I gave you guys. I believe this is directly from Dr. West's PowerPoint, and I want you guys to know a couple of things. So I color-coded them, but I'm still going to draw these lines to differentiate things. So here we have our ortho-para activators, and as someone mentioned earlier, you can think of all activators as being ortho-para directing because that's just how they are. If it's an activator, it's going to direct ortho-para. However, some deactivators can also be ortho-para directing, and that is the halogens. And we are going to call these the weak deactivators. And meta deactivators we're going to call strong deactivators. And what you guys have to really take away from this list is that NH2 is the most reactive group. It's going to make the benzene ring super active. And the reason for this is that it is the most willing to give up its electrons. Very basic. So it's going to give its electrons and allow the benzene ring to be more active. After NH2, we have our OH groups or our OR groups. Those are pretty much the same on the reactivity scale. OH is just a little bit more reactive. And then after that, we have kind of our weak ones because these do have a carbonyl, so that means most of the electron density will go that way. However, some of it will still go into the ring. And then our R groups are just going to donate by electronegative effects. So we know that this is the weakest activator. Again, you do have to know the order, most to least reactive. That's why I'm kind of going through these little cheats to help you guys. So again, NH2 is going to be the most reactive. And then we can see the trend. After the nitrogens, we have the oxygens. After that, we have the ones that have carbonyls. And then the weakest activator is going to be the R group. And then we know the halogens have their own category. They're deactivators, but they're ortho-para directing, so they're weak. And then our strong deactivators, the strongest one is going to be NO2 because it has that positive charge on the nitrogen. Sorry. So that is going to be our least reactive, aka our strongest deactivator. And then here when we look at it, carbonyls are going to be strong deactivators, but they're going to kind of be the weakest of the strong deactivators. And then we have SO3H. And then we have CN. This one has a triple bond. And then we have NO2, which is the strongest deactivator. Super deactivating. And then someone said, so under your Friedel-Crafts limitations, it should be NO2. So that's a great point. So Friedel-Crafts will not happen with any of these, but it also will not happen with NH2, even though it's not a deactivator. So that's a very valid question. Everyone always gets confused by that. So the reason it won't react with NH2 is because instead of having an electrophilic aromatic substitution, you're going to just get a regular old acid-base reaction. So we call it no reaction. So I will make a little note here, though. Friedel-Crafts can happen with all of these. Better shut up. Good? Any questions?
I have a question.
Yes, go ahead.
So, like on the least reactive side, like the one closest to the halogens, could you say that that's the weakest deactivator or no?
So that's what I almost accidentally said. We can think of it as the weakest strong deactivator just because we know that this is the weakest deactivator. But out of the strong deactivators, this one is the weakest. Did that answer your question?
So the halogens is the weakest.
Yes, exactly.
Okay, thank you.
You're welcome. Okay, so we have like 2-ish minutes left. So we're going to do some examples. So let's say we have this right here, right? If we have Br2 and FeBr3, what are we adding to our benzene ring? A bromine, exactly. All right, so this R group, is it donating? What is it donating or withdrawing? It's an electron donating group, exactly. So is it going to be an activator or a deactivator? Yes, it's going to be an activator. And since it is an activator, is it ortho-para-directing or is it meta-directing? Ortho-para. Exactly. So this is an ortho-para activator. So that means this carbon, and this carbon are likely to be substituted. So we can have multiple answers here. I'm only going to draw 2 of them because the 2 ortho answers are essentially the same. And that is one ugly benzene ring. I apologize. And I know I don't have to call it out every time it's ugly, but it's just a rosemary thing. Okay, so we could either get the para answer or we could have the ortho answer. And as I kind of mentioned last time, these are both equally as likely. Dr. West says it's a 50-50. Questions? All right, so what about this one? Is this an ortho-para-director or is it a meta-director? Meta, and that is because it is a what? Activator, weak deactivator, or strong deactivator? Strong deactivator. And then someone asked a question that I did not see. So let's scroll up a little bit. Okay, so someone said, like, for exam questions, the ortho and para will both be correct. Yes, so if he asked you which of the following are possible answers, both of those could be correct. It's possible that he only gives you one or the other one. That's fine. But if he said, show all of the following answers, they both have to be there because those are both possible and they're equally likely. Okay, so in this next one, it is a meta-director. So that means we are going to go here or here. So there's really only one answer because both meta positions will give you the same product, essentially. So NO2. And if we have SO3H, what is going to be added to our benzene ring? Oh, and someone raised a good question. They said, I thought it would be no reaction because it's a strong deactivator. So that would only result in a no reaction when we have Friedel-Crafts. So even though this would be a lot harder to react since it's a strong deactivator, it's still possible. The only time it's not at all possible is in the case of Friedel-Crafts. Ooh, and we got a couple different answers to my question, what's actually going to be added, and I was kind of expecting that. So be very, very, very careful for nitration and sulfonation. You have to know my handy dandy thing. So for nitration, the group is HNO3, but you're only adding an NO2. And for sulfonation, it's SO3, but you're adding SO3H. Make sure you review that a couple times because he will definitely try to trick you by adding the wrong group. Like he'll have one answer choice that has SO3H and the other one will be like SO3. The other one would possibly be like SO2, whatever. So in this case, we are going to add SO3H. And the last one we're gonna go through today because we are technically overtime. What is this group considered? Is it ortho, para, or meta? Yes, it's a halogen. And yes, okay, so it's an ortho para director. And it is a weak deactivator. So remember, halogens are the only ones in this special weak deactivator category. They are ortho para directors and they are deactivators. So, what reaction is this? Friedel-Crafts alkylation, exactly. So whenever you have a Friedel-Crafts, you have to be careful. Is Friedel-Crafts going to happen with a weak deactivator? Yes, it totally could. So we could either add here, here, or here. So we could have two answers. Wow, the benzene rings just keep getting uglier and uglier. And in this case, we can't really have any kind of rearrangement because this is what our carbocation would look like. So in either case, we're just going to add this group. And ta-da! This is our ortho product, and this is our para product. And then someone had a question. And I'll answer that question in a second. Okay. Any questions? Someone said we don't add a chlorine. No. So we're not going to add a chlorine because this chlorine is going to be our leaving group. This is an alkylation, so we're only going to add the carbon chain. Oh, you're so right. I forgot to draw a carbon. Yes, we do have two carbons. Thank you. And since someone asked, we can just look at this next one. So what kind of group is this? Activator or deactivator? Yes, it is a strong deactivator, which means it is a meta director. But before we do any of that, what kind of reaction is this? Yes, it's a Friedel-Crafts acylation, and so Friedel-Crafts cannot happen with a strong deactivator, so this would be no reaction. And I can zoom out so you guys can take a look at that. You're very welcome. Okay, so I will let you guys go. Let me know if you have any questions, comments, or concerns. Oh, and if you guys are still here, I'm doing a Halloween party lame thing right after this for like an hour. It was a lot more fun last year because we were in person and we did a costume contest. But Bear is here. He's going to have fun. If you guys just want to chill, play some games, whatever, I'll be here. So it said, how is that an electron withdrawing group? So it's an electron withdrawing group because these electrons will go out towards the oxygen, not towards the ring. So it's taking electrons away from the benzene ring. Cool. Any other questions? You're very welcome. Have a great weekend, guys.